for being here today. And we have Dr. Nguyen Lam. He's assistant professor at Memorial University of Newfoundland, Greenfield campus. And the talk you can see on your screen is about sharp uncertainty principles. So please, your time, Dr. Lam.
Thank you everyone for being here at this early morning. I know it's kind of painful, but yeah, thank you again for being here. So Dr. Hoa actually told me so many good things about choice, about Trojan math seminar. So that I would like to present a talk here, and also I wish I can visit choice someday. And actually, I told Dr. Hoa before, but actually it's kind of destiny for me to present the talk at this day and at this time, because usually on Thursday at this time slot I have to teach. But this year, begin from this year, Canada has a new holiday, and it's on this day. So that's the reason I am free and I can give a talk right now. But anyway, let me start. So today I will talk about the uncertainty principle. So this uncertainty principle is kind of one of the most famous feature in quantum mechanics. But I'm not an expert in quantum mechanics, so I will not present the talk in that direction. Instead, I will talk in mathematical point of view. So this talk is based on John work with. So John worked with Cristian Cazacu at University of Bucharest and Joshua Flynn at University of Connecticut. Okay. So first of all, let me talk a bit about uncertainty principle. So uncertainty principle is kind of at the foundation of quantum mechanics. And when usually in quantum mechanics, when we say the term uncertainty principle, usually people refer it to the Heisenberg uncertainty principle. Heisenberg uncertainty principle. And basically it claimed that the Heisenberg uncertainty principle claimed that we cannot measure the position and the velocity of an object exactly at the same time, even in theory. Okay, so we cannot measure the position and the velocity exactly at the same time, even in theory. One of the mathematical formula for that is the uncertainty in position times the uncertainty in velocity greater than or equal h over 4 pi, where h here is the Planck's constant. Okay, and the Planck's constant is around 10 to the power minus 34. So that's the reason the uncertainty principle here cannot be applied to the real normal life, because the error in this case is too small. It's too small. So it's not true. I mean, because it's too small, it's insignificant in the real life. So that's the reason in the real life we still, in the normal life here, we still can measure the position and the velocity at the same time. But in quantum mechanics, this number is significant. That's the reason the error in position and error in velocity is always greater than or equal a significant number. So that's the reason we cannot measure the position and the velocity at the same time. Okay. Okay, so in this talk, I will focus on another mathematical formulation of uncertainty principle, and the one which I would like to mention on is the following one. So for any function u in suitable space, and for now let's choose that to be C0 infinity of Rn, and the dimension is greater than 1, then the format the mathematical formulation I want to use is this one. X square u square dx, okay, greater than or equal to some constant u square dx square. Okay, so this is the Heisenberg uncertainty principle formulation I would like to use. So let me explain this a bit. So basically, in quantum mechanics, this is only one. Okay, so in quantum mechanics, this is one. So this is constant. On the left hand side, we have constant because usually it's one. On the right hand side, you can see this one is the second moment of the position. So this is the uncertainty in the position. And for this one, if we use the Fourier transform, this will be the integral of some say square and the Fourier transform square. Right? So this will be the uncertainty in position. Okay, so basically that's another translation of the uncertainty principle. Okay, so in this talk we mainly focus on the constant here. We would like to understand the best constant, and also we would like to find out the optimizer for this inequality. Okay, so this one without the best constant, it's not hard to prove. It's not hard to prove. For example, if we use the Hardy inequality, so Hardy is the one Hardy inequality. So Hardy is the famous mathematician with I put a quote here. And so if we use the Hardy inequality, we claim that the gradient square greater than or equal n minus 2 over 2 square integral of u square over x square. Okay, so in mathematical physics, usually they understand the Hardy inequality at that the operator minus Laplace loss n minus 2 over 2 square 1 over x square. This operator is non-negative. Okay, so they are equivalent. Okay, so anyway, if we use this Hardy inequality, then we can prove the Heisenberg uncertainty principle easily without the best constant. For example, by applying the Hardy inequality, we have this one. First of all, if we apply the Hardy inequality, it's greater than or equal u square over x square dx. And for the second one, x square u square dx. And now if we apply the Cauchy-Schwarz Holder inequality, it's greater than or equal integral of u over x times x u dx square, which is sorry, I think I missed the constant here. This is n minus 2 over 2 square. So this is n minus 2 over 2 square. So this is n minus 2 over 2 square u square. with x, right? Okay. So if we use Hardy inequality, we get this one with the constant n minus 2 over 2 squared. In general, this constant is not self. For example, when n equal 2, this constant is 0 when n equal 2. So that means we have nothing. Right? When n equal 1, somehow, incidentally, when n equal 1, the constant is self. But when n is greater than or equal to, the constant is not self. So actually, and I will show later that actually the constant, we can get the self constant Cn equals n squared over 4. Okay, this has been proved by many researchers, and I will also explain later why do we have this one. In short, the best constant can get up to n squared over 4, and moreover, we also have the minimizer, optimizer, and the optimizers for. So when I say optimizer, I mean that means when we plug into the inequality here, we get equal. So that's the meaning of optimizer. And in this case, the optimizers are the Gaussian profile. So it has the Gaussian form for x equals alpha e to the power minus beta x squared for positive beta. Okay, so this is the Heisenberg uncertainty principle. Okay, I also want to mention another uncertainty principle in physics, and that is the hydrogen uncertainty principle. And the formulation of the hydrogen uncertainty principle is gradient u square multiply u square dx greater than or equals some constant, again u square over x dx square. Okay, so the term hydrogen, the hydrogen here comes from this one, because this is kind of the atom of hydro. So of course, again, we can use Hardy inequality to prove this inequality without best constant. But we will show later the best constant here will be n minus 1 over 2 squared. Okay, so we will show later. Okay, so basically in this talk, I will focus on these two uncertainty principle, the Heisenberg uncertainty principle here and the hydrogen uncertainty principle here. And mainly I will focus on the sub constant and the optimizers of the two uncertainty principles. And by the way, we will show later that n minus 1 squared over 4 here is sub, and optimizer are of the form ux equal alpha e to the power minus beta x, and beta is positive. So you may wonder that in the starting space of our function is C0 infinity. That means the smooth function, and has compact support, right? But the minimizer is not. Minimizer here is not, because the minimizer here is smooth. This optimizer is smooth. But this optimizer doesn't have compact support. But basically, we can always use the density argument to approximate C0 infinity here to a larger space, and then the minimizer belong to that larger space. For example, we can do that we can let C0 infinity here to be dense in some sublab space, maybe W12, or maybe swatch space. So I mean, there are many options to do so. Okay, so the first result I would like to report is actually the Heisenberg uncertainty principle here. The Heisenberg uncertainty principle here, and the hydrogen uncertainty principle here belong to the famous Caffarelli-Kohn-Nirenberg inequality. Okay, so they belong to this famous Caffarelli-Kohn-Nirenberg inequality, so this Caffarelli-Kohn-Nirenberg inequality, they are very general, and they generalize a lot of well-known inequalities like Sobolev inequality, Nash inequality, Nirenberg inequality. So there are a lot of well-known inequalities, and they very general. But the form I would like to focus on in this talk is as follows. This one to the power 2b u square over x to a greater than or equal some constant depend on a and b of u square over x a plus b plus 1 square. Okay, so you can see that if we choose b equal 0 and a is minus 1, we have the Heisenberg uncertainty principle. And if we choose b equal 0 and a is 0, then we have the hydrogen uncertainty principle. Okay, so Heisenberg uncertainty principle and hydrogen uncertainty principle, they belong to this Caffarelli-Kohn-Nirenberg inequality, especially in this subclass, this subfamily of Caffarelli-Kohn-Nirenberg inequality. Okay, and about the best constant of C square and AB here, best constant NAB here. So in I think in 2007, I think Costa flew in JMIA. Costa used the following very simple method to study the best constant. So he start from expanding the square. So he just expand this way. X a plus 1 u. So he expand this way. So of course this one is always positive, right? Because we have the square here, and then he just expand this. He just expand this one, just square, and then using integration by parts and so on, and he get the following. We can do this easily to get u square to the power 2b, and of course it also have t square integral of u square over x to a. Right? And for the middle term, we have gradient u times u, but we can use integration by parts to get minus n minus a plus b plus 1. Okay, the reason we get the middle term is because integration by parts. So u square over x a plus b plus 1. Okay, and now the argument is this is true for any t. It is true for any t, and this is nothing but a quadratic equation. The quadratic equation t square here, t here, right? The t square here, t here is because it's always positive. So by a very elementary result. We know that the discriminant delta, which is b square, some b square minus 4ac, right? Is always negative, right? Because the quadratic is always non-negative, so the discriminant is non-negative, right? And so that means in this case, b is this one, right? A is this one, A is this one, and C is this one, right? So, and because of that, he get n minus a plus b plus 1. Right? So, n minus a plus b plus 1 square over 4 less than or equal u square over x to b, x u square over x to a dx. I missed something, so move it to this, and integral of u square over x a plus b plus 1 square. Okay, so he basically he can prove using this very elementary approach. He can prove that that the inequality here holds with c n square to be this one. Okay, and at that time Costa thought that this is the best constant, so he claimed that c a n b, which is absolute value of n minus a plus b plus 1 over 2. Here is sharp, is the best possible. However, after that, he realized that there is a mistake. Because this constant is not sharp. Actually, this constant is not sharp for some values of a and b. So this constant is actually optimal for some a and b, but not always. So after that, he realized a mistake in his paper, and then he fixed that. He fixed that in another paper by Katrina and Costa in 2009 on journal on differential equation. So in this time, they fixed the error, and they basically proved that the best constant is n minus a plus b plus 1 over 2, and on some domain A, and c of n a b equal n minus 3b minus a plus 3 over 2 on some domain B. Okay, so it depends on A and B for the best constant. Okay, so this the method, the new method they use in this paper is very different than this simple method, because this is a very simple one, the very simple elementary one. But for the new method to fix the error, they have to use many tools in analysis. For example, first of all, the method they use is first of all, they use a chain of variable. So a chain of variable into cylinder, into the cylinder. So Sn minus 1 plus r. First of all, they chain that. They use the chain of variable into the cylinder, and then after that, they use spherical harmonics. spherical harmonic decomposition. And finally, they use a Kelvin type transform. Okay, they use the Kelvin type transform to okay. So after we read these two papers, we feel very kind of annoying because to fix the error, that error, they have to change from the very simple method here to rather complicated method here. So that's the reason we decide to go back to the paper by the origin, the first paper by Costa. We decide to go back to this paper, and at that time we asked them, and we asked ourselves, what's wrong with this one? What's wrong with it? Why it doesn't work in some? Why it does work? This method works for some cases, but why in the domain B here, why it doesn't work? Why that? And after we read this paper carefully, we realized that probably at that time Costa missed another term in here. That means probably we should add another term to the square here. So we decide to do that. So we decide to go back to Costa paper, and we decide to add another term. So we use the same approach as Costa, but at this time we add another term. So we use the same one, the term 1, so x over x a plus 1 u. So this is the original Costa term, but this time we add another term. So x over xc plus 1 u. We decide to add another term and expanding the square, expanding this square, and after just expanding the square and simplify, we realize that this must be b. Okay, we decide this must be b, so that everything will match up. So we expand this one, and if we expand this one, then there is another term. So if we expand this term, this will be like normal 1. This is x2b. This is the one like before, but this time we have an extra term to s minus n minus a plus b plus 1. I mean, just use the same like Costa method. U square over x a plus b plus 1 dx. And of course we have like before, d square u square or x to a, and we have extra term s minus n minus 2b minus 2 u square over x to b plus 1. Okay, so the reason, so again, at first we put here c because we don't know which value should we choose. But after that, to have this term here, we have to choose c to equal b. Okay, but because of that, we have the extra term, this one. Okay, and then because in the Caffarelli-Kohn-Nirenberg inequality here, in the original Caffarelli-Kohn-Nirenberg inequality here, we don't have the last term. We just have 2b here, 2a here, and a plus b plus 1 here. So that's the reason we have to choose, set that this one to be 0. Okay, because we don't have this term in the inequality. So we choose s to be 0 or s equal n minus 2b minus 2. And somehow when s equals 0, we get the best constant. I mean, use the same method because in that case, this one disappear. This one disappear. So again, we have the quadratic equation here in t, in the variable t, and it's always positive. So again, the discriminant must be negative. Use the same method as before. But this time, when s equals 0, we get n, a, b, either original constant constant. And when s equals n minus 2b minus 2, then we get the new constant. We get the new constant. C n a b is n minus 3b minus a plus 3 over 2. Okay, the reason is because this 2s here. When s is 0, it's nothing. So this becomes the original constant. But when s is this new one, the constant he changed. And we have the new constant. And because of that, the best constant is just the minimum between the two. So, and minus 3b minus a plus 3 over 2. And if we compute this constant, it's exactly the result, the later result by Costa and Katrina. It's exactly this one. Okay, so basically, we fix the Costa error. So we give a simple proof. We gave a simple proof for the result by Katrina and Costa. But after that, we realize that we can do better. We can do better because the reason is because basically in this proof, the main tool is just integration by part. So after that, we ask ourselves, what if we change here to something smaller? Because this is a vector, basically this is a vector. So at a time where we ask ourselves, what if we multiply this vector by a unit vector? So we decide if we multiply everything by the unit vector. Okay, it's smaller. So the result we will get a smaller term. For example, for the first term we don't get this one anymore, but we get this one, which is smaller. And actually, in the polar coordinate, this is the radial derivative. This one is the radial derivative in the polar coordinate. So gradient is the full gradient, but in the polar coordinate, this one is much smaller, and this is just the radial derivative. Okay, so at that time we decide to go back and add this term to here, and we achieve the result. We achieve the new result that the integral over Rn of x over the norm of x dot gradient u square over x to b. Integral of u square over x to a dx greater than over c square n a b u square over x a plus b plus 1 square. Okay, we achieve with the same c n c square c a and b here, with the same c and b here. Okay, so we have the same constant. It's just that now our first term is smaller. Instead of the full gradient, now we just have the radial derivative here. Okay? And the motivation why we put the radial derivative here is because gradient is not well defined in some spaces, in some manifold, especially in some groups. And at that time, we have some projects on the homogeneous groups. And on the homogeneous groups, we cannot define the gradient. We cannot define the full gradient here. So homogeneous group is kind of Lie group with some special structure. In that, we cannot define the gradient, but we can define the radial derivative, and the corresponding radial derivative of the homogeneous group on Euclidean is this one. Okay, so that's the reason we decided to put this. But anyway, we can see that easily that this one is less than the full gradient, right? This is less than this one because this is the unit vector. Okay, so we have this out. We have the first result here, and this result has just published on by Cazacu, Flynn, and myself on JDE, differential equation in 2021. Okay, so basically, we try to give us new and simple proof of the result by Katrina and Costa, and by the same time we try to improve that to this one. And because of the approach, because the approach is very simple, we just expanding the square. So to find out the optimizer, all we have to do is to solve this ODE. Okay, so we just to find out the optimizer. That means if we want the equality, so we just need to solve this to be 0. And when we solve that, we can find out the optimizers. We can find out all the optimizers. Okay, so in Katrina and Costa, somehow they can find out the optimizer, but they don't know if they are all the optimizer or not. But because of this simple approach, now we can solve that for all optimizers. Okay, and yeah, I will not write down the optimizer here, but basically if we have the Gaussian profile form, so e to the power minus something. Okay, so that's our first result. Okay, so after that, we find out in another paper by Maja. So Maja in 2018, he has a paper, and the title of the paper is 75,000 unsolved problem in analysis and BDs. So Maja in 2018, he wrote a paper, 25,000 unsolved problem in analysis and BD. So there are a lot of open problems there, and especially in problem 9, he asked the question. So what is the best constant C star n in the inequality? In the inequality gradient u square. Now this time he put a vector. Okay. So basically he asked what is the best constant in the uncertainty principle, in the Heisenberg uncertainty principle. But this time they put a vector. Where the vector here is u1 to un is divergent free vector field. Okay, so the reason he asked this question is because divergent free vector field is used a lot in fluid mechanics, Navier-Stokes equation. So that's the reason he asked this question. What is the best constant if we replace the scalar function u? We replace the scalar function u by vector, and that vector is divergent free. Okay. Of course, if we don't have this condition, if we don't have this divergent free condition, it's easy because if we just have the regular vector, then we can use the Cauchy-Schwarz inequality, right? We can use the Cauchy-Schwarz inequality. So I mean, if we just have u is a vector, then we can use the Cauchy-Schwarz inequality to prove that C star n here is just the regular best constant of the Heisenberg uncertainty principle Cn over 4. So this is just the Cauchy-Schwarz inequality, right? Because you know this is nothing but sum of ui square, and then the inequality is like the sum of ui square, and then the sum of x square ui square, and by Cauchy-Schwarz inequality greater than or equal the sum of gradient ui square x square ui square, right? Square root, right? I mean, I should put the square root here, right? And then using the classical or Heisenberg uncertainty principle, we can find out that easily this one. So the difficult one in this case is the condition divergence-free vector field. Okay, so when we read this question, so we don't know how to answer this question. Now we don't know how to answer this question, but at least we know that by the above argument, the new base constant here must be greater than or equal to n squared over 4. Right? So at that time, when we read this question, we told ourselves that okay, maybe we can try for some special case first, and that's the reason we try for n equal to first, just 2 dimensions. For simplicity, we try for n equal to, and when the point is when n equal to, we can always show the vector u is u1, u2. So in this case, we can always write a divergence-free vector field. So divergence-free vector field, we can always rewrite the divergence-free vector field in this form. Okay, for divergence-free vector field. Free vector field. We can always rewrite the divergence-free vector field in this form: minus d phi over dx2 and d phi over dx1 for some scalar function phi. Okay, and if we do this, then by direct computation, the gradient of the vector field is just the Laplace of phi. Okay, we can compute this easily. We can compute it directly. This is just true. This is true because we have no way here, and we can use integration by part. Use integration by part to get this one. And similarly, we can write down the gradient of the vector field. We can write down the vector field. So in this case, Maja question is equivalent to. So Maja question is so the Heisenberg uncertainty principle for divergence-free vector field is now equivalent to the following question: x gradient phi square greater than or equal to some base constant of gradient phi square. So that means the Heisenberg uncertainty principle now is equivalent to the second order Caffarelli-Kohn-Nirenberg inequality. Okay, but this is just true for again. This is just true for R2 because this is in dimension 2. Because just in dimension 2 we can write in this form. Okay, just in dimension 2 form. But in general, when with a vector field U has the form gradient of some function, if a vector is the gradient of some function, we can always write like this for any dimension. But you must have this form, okay? Especially when n for the two-dimensional, when for two dimensions, when R2, then divergent-free vector field has this form. But in general, if we have this form, then we can change Maja question to this inequality. And in general, a function is the gradient of a vector of some scalar function, then you will be curve-free. Curve-free, and basically it is equivalent. Okay, it is equivalent. So if a vector is curve-free, then we can always write u as the gradient of some scalar function, and then we change the problem to the second order Caffarelli-Kohn-Nirenberg inequality. Okay, so we decide to follow this direction. So now we change the Maja question to the Heisenberg uncertainty for curve-free vector field. We want to show this, and basically we have to find out the best constant in this inequality. Okay, so now we have to find out the best constant in this inequality. Okay, so and the method we use to study the best constant is to use the spherical harmonic decomposition. So we use spherical harmonic decomposition. So that means we can write a function u, a function phi here. We can find the function phi here, phi x here in the polar coordinate is a phi of r sigma, and we can always write this in the sum of some function in R, some function in R, some function in R, and a function in the angle. Moreover, the important thing here is this one, the angle here, form an orthonormal basis in L2. Okay, so that's the key thing. So phi k here is an orthonormal basis in L2 of the sphere. Okay, and because of that, we can compute everything here. Because of that, we can compute everything here in terms of pk only. Okay, and the point is, if we compute everything in terms of uk, now we just have the variable r here, and which is one variable. Okay, so basically, using spherical harmonic decomposition, we change the problem to the question here to one-dimensional question. So we change this using spherical harmonic decomposition. We change it to the following. For some vk, we do some other change of variable. But anyway, the idea is using spherical harmonic decomposition. We change this one to one-dimensional inequality, and minus 1 plus 2k 0 infinity and plus 2k minus 3 vk prime square multiply. So this is the first term. This is basically the first term. Okay, of course we have the sum, but after using the Cauchy-Schwarz inequality, we don't need, we can throw away the sum there. So this is the second term, vk prime square minus 2k vk square dr, and greater than or equal c star n 0 infinity and plus 2k minus 1 vk prime square dr. Okay, so the Maja question now, for Maja question on dimension 2 now is equivalent to this first this one-dimensional inequality. Okay, the point is it has so many terms. So we have 2 here, we have 2 here, and we have 1 here. So to deal with that, we begin by removing this term. So we remove this term using, so we use basically we use half D, so one-dimensional half D, and combine with the one-dimensional Caffarelli-Kohn-Nirenberg inequality, and we prove that C and K here, the C star NK is 1 minus AK over n plus 2k square and plus 2k plus 2 square over 4. Okay, so we prove this inequality for this constant is this one. Okay, and so the C star n, the best constant in Maya question, is just the infimum over k up on this. So k equal 0 up on this square over 4, and so we have the result, and this one we can compute this constant. In particular, we answer Maya question for n equal 2. So this is our John paper submitted. We have just submitted this paper 2021. So we answer Maya question. Then see the Maya question when n equal 2. This is 4. Okay. I just want to remind you that the best constant in the Heisenberg uncertainty principle is n squared over 4. So when n equal 2, the best constant is 2 squared over 4, which is 1. And now if we change from scalar function, which is 1 here, to divergence-free vector field, the best constant now is 4. Okay, so this is our result. And I think time is up, so I think I should stop here. Thank you for your attention.
And thank you very much for your interesting
Thank
talk.
you. Thank you, folks.
Yeah, now let's ask the audience, if they have any questions for you. It seems like Sergey and Dima have questions.
Sure, I enjoyed.
Quick comment. I mean, great analysis and enjoyed the talk.
Thank you.
I wasn't familiar with Mazia's paper with, so many open problems, but
it's just 75,000. Yeah, so there are a lot.
Yeah, I mean, 1,000 were in parentheses, but even 75 is a lot. But this is 2018, right?
2018, yes. 2018. So actually, Maya basically he collected on the unsolved problem. And the problem he cannot solve from his teens up to now. Put everything to that. So 75,000. Okay.
Good God, that's a lot of problems.
I mean, there are lots of open problems. If you want to try, then take a look, big one, and try.
Dima, do you have questions for him?
Yeah, very interesting talk. I enjoyed it very much. Thank you. So the question that I have is whether there are applications of these inequalities to the standard PDE questions of well-posedness, like.
Yeah. So first of all, the first one, the Caffarelli-Kohn-Nirenberg inequality. So yes, so Caffarelli-Kohn and Nirenberg, they try, basically they prove this one to study the regularity of the Navier-Stokes equation. So basically they use this to study the Navier-Stokes equation. And for Maya question, actually at that time, we just try Maya question. We don't really understand the meaning of that. But after reading, then it seems people use Maya question to study the regularity in the fluid mechanics. But we haven't. So I'm not expert on that, so I don't know. But it seems that they use for fluid mechanics. But again, like I mentioned before, in fluid mechanics, they like the condition, the divergence-free condition. So divergence-free condition here. But basically, in our reason, we just show that we just answer the question for n equal to 2 only. And for general n, we just have the answer for curve-free vector field. And actually, I don't know, not yet. At least we don't know any application in business for curve-free vector field yet. So it will be, I mean, our goal. It will be better if we can answer the question for divergence-free vector field for general n, but not now.
Thank you. And the weight x squared kind of reminds me of Pakhajaev identity.
Yeah.
So that can go the other way, non-existence of solutions.
Right. Yeah. Yeah. Maybe that's another way to think about Pakhajaev, right? Yeah.
Thank you.
Thank you. Thank you.
Do you have any questions, Sergey?
I think Sergey just asked about 75,000.
I don't have particular questions, but like I said, I really enjoyed the talk. It's been a while since I listened to something like that, and classical analysis resulted with applications to, you know, as far as application to Navier-Stokes, you know, it will be 75,000 people doing Navier-Stokes equations. I'm sure one of them will find the usage of this inequality.
So,
but as far as the divergence-free vector fields and curl-free, yeah, it's really interesting. I mean, if it can be done for like general vector field, or I don't know, it sounds big.
So the reason we choose this question, the reason we choose this question is because in 75,000 questions there, this is the seems it looks the most easiest one. So okay, we chose this one to try.
Right.